Okay. All right. So I would like to welcome everybody. Thanks for joining this morning. It's a holiday. Thanks for taking the time off. Sorry, give me a minute. Yeah, so this is an open house session we are doing. It's being organized by BAS. As you already know, it's Bangalore Astronomical Society. So it's a non-profit organization. We are a voluntary-driven group. We like to promote astronomy and science and related topics. So we do outreach activities, we do sessions and all sorts of things. So this is a part of one of the things we wanted to do. This is an open house. I'll come to the agenda in a minute. Um, so just to introduce myself, my name is Satish. I've been with BAS for I think more than 6 years now, and I've been part of a couple of start party sessions and few talks. And by profession, I'm into IT. I manage tech teams. I've been working in the industry for more than 20 years, and that's about me. So today I'll be moderating this event. Um, it's interesting because this is my first time moderating, so apologies if I miss out on anything, but I look forward to a good interactive session. So I'll be the mediator in between the audience and the panelists. So just to take a step back, what we wanted to do with these sessions was to actually, so BAS has grown a lot in the last few months. We have almost 500, more than 500 people now, just on the Telegram group. And most of the times we see there's a lot of discussion that happens, but I'm sure there are a lot of people who are beginners and who could be getting left out. So the idea of the open house session, and we want to do more in the future, the idea of the open house session is to give the beginners a chance to actually ask questions and clarify whatever they want to know. So there is no standard or there is no strict agenda that we want to follow. It's an open house. That's why we're naming it as open house. So that's the idea of this session. And it's going to be focusing more on beginners, especially at least for this time. In the future, we'll see how it goes, right? Also, another thing I want to mention is we'll probably focus on all the topics, anything and everything related to astronomy, except for photography. So any questions on astrophotography you may have, I would request you to hold on to that because we will do a separate session on astrophotography because I know I think that it's a topic where a lot of people are interested. So we thought it deserves a separate session by its own. Yeah. So this time for this session will exclude astrophotography. Yeah. So that's the agenda of this session. And the way we'll do this is we'll do this in two parts. We'll go over. Um, we have picked up some questions from the list of questions that people had submitted on the Google form. So we'll go through some of them, if not all, and we'll try to have a discussion around that. After which we'll open it up for questions from the floor. You can either use the live feeds to submit your questions, or you can just unmute and place your question when we start the Q&A. So that's the agenda. We'll try to keep it under 1.5 hours tops, somewhere between 1 hour to 1.5 hours, but we'll see how it goes. Yeah. So that's a brief. And before I invite the panelists and we start the discussion, is there any questions, any clarifications anybody wants before we get started? Okay, I'll take that as a no. And but let's keep this interactive. I think it'll be good to the intention was to really understand what are the kind of questions you have in your mind. So that way we can make the best use of the time and the panelists that we have, and also the future sessions, right? Okay, so with that, then let me introduce the panelists. We have got 4 panelists today. Very excited about this. So first, I want to introduce a call upon Naveen. So Naveen has been is one of the founding members of BAS. He's been there for a long time, of course, and he's a science educator and also a leadership trainer. He has appeared on TV several times. So welcome, Naveen. And
Hey,
next we have.
good afternoon, Satish. Good afternoon to everybody. Nice to be here.
Hi. Looking forward to a good discussion. And Naveen is He is knowledgeable on many fronts. So I really hope we leverage this time. Next, I want to introduce Akarsh. I don't know if he has joined yet, but if not, he'll be joining soon. So
Hi,
he's
yeah, I'm
based.
here.
Hey, Akarsh. So
Yeah,
Akarsh
hi.
is Hey. So Akarsh is based out of the US. He's a PhD in physics. He has a PhD in physics, and I think he's one of the developers of K-Stars, which is the planetarium software. So Akarsh, is very excited to have you here. And I'm, again, a ton of information and knowledge out there, so which I hope the audience can leverage. Um, I want then invite Vishwa. Vishwa has again been part of the group for a long time. A lot of sessions. I know I think he does a lot of sessions for schools and colleges throughout the year. Welcome, Vishwa. And last but not the least, I want to invite Shashi. Again, been part of the group for a long time, done a lot of sessions with colleges and schools, and he's very knowledgeable on many areas. So welcome to everybody. Okay, so I want to kickstart the discussion. I have 4 or 5 themes that I'll want to go through, and want to start off with an icebreaker. And pretty much, I'm sure a lot of people will have the questions in their minds. Is how did you? And I'm going to pass this question one by one to all of you, and wanted to hear from you. So, how did you start astronomy? How did astronomy happen for you? How did you get into the hobby? What are the kind of instruments that you have used, and how has your journey been, in short? So maybe Naveen, if we start with you.
So my journey with astronomy started off way back in 1992-93. Okay, that was when I was probably in the high school, and during my high school class, there was a syllabus change in our science books, and astronomy was just introduced, and that created some interest in me. And that was the time when I had been to my native place for the vacations of after the college schools, and that hooked me up into the night sky, because the first problem that I had with the night sky is I could count so many stars and there was no end to it. So my first astronomical question was why there are so many stars and why am I not able to count them? Every day I used to check this out, like my count was going on to few hundreds and I was getting confused. Did I count the star? And when I started digging deeper into why am I not able to count the number of stars, and if I had to count, how many would it be? That was my first question. During the same period in 1993-94, there was a huge buzz around the comet Shoemaker-Levy 9, which was about to hit the planet Jupiter. And there was not a single newspaper which did not talk about it. And I became a big fan of the comets, and I started collecting all the information related to comets. And the interest into the comets, the night sky, the beauty of stars, and the whole problem of unable to count the number of stars led me to planetarium, Jawaharlal Nehru Planetarium, where I met Dr. Shailaja. And I still remember I had a 100-page book in which I had written more than 50 questions. And I kept this book right in front of her and I asked her, "Ma'am, I need answers to all these things." And that was the start of my astronomy. And soon I realized if I have to learn more, I need to teach more. So my mission became learn to share, share to learn. And from then onwards, from 94 onwards, I started sharing my learnings in astronomy to my team members, my class teams, and then to the schools and colleges which I studied, and eventually got onto the astronomy. And it was in BAS in 2006 when we started this, that learn to share, share to learn became a next step where we had to visit a lot of colleges, universities, and do the same thing. And that is how we get started. And I'm glad to be associated with that exploring space. Thank you.
Awesome. That's great. I hope you got all your answers, whatever you had written in that book. But I completely agree. I think that's a very good thought. If you want to learn something, the best way to learn something is actually to teach. I think it's I completely agree with that. It's awesome. Akarsh, over to you. How did it happen for you?
So I was in, I think 10th standard, and I came across this astronomy program called K-Stars. I was a computer nerd, not an astronomy nerd. I thought astronomy was very boring because it involved memorizing the masses and properties of the planets. So I never liked astronomy, but I found this software called K-Stars, and then I started looking at its map, and then I went up at the terrace of the house we were living in, and started matching the constellations and the stars. And I was very amazed that you could match what was shown on that program with the sky, and that really sparked my interest. And at the same time, I stumbled upon a book that was sitting in some bookshelf at home on astronomy. I forget who the authors were, but it was one of those popular books with a lot of very beautiful pictures. And I had heard about things like North American Nebula and Pelican Nebula and all of that. And even this software showed things like Beehive cluster and so on. I really wanted to see what these things are. And I used to go up to the terrace and be disappointed that I didn't have anything to see all of this with. Incidentally, at the same time, I found that a few friends from my school, just as I finished 10th standard, I found that few people who were entering 10th standard, they were going to the planetarium to make a telescope. So I was very excited, saying I too want to make a telescope so I can see what this Beehive cluster is. And that's how it happened. Then I went to ABBA, Association of Bangalore Amateur Astronomers, learned a lot over there, ground my first 8-inch mirror. And that 8-inch telescope became a craze. Around the same time, I was not one of the original founders of BAS, but I was there in, I think, the second meeting or something like that. So BAS happened, and the next 4 or 5 years were very intense astronomy, to the point where I think we would probably have gone 30 times to a dark sky site in a year, whether it is cloudy or not, just to hope for like 1 hour of clear sky. And this is also used to be by bus. And so I really got sucked into visual deep sky observing. And eventually I gave the 8-inch away to get a 17.5-inch. And then I moved to the US, and here I purchased an 18-inch telescope secondhand, which is what I observe with. I would say my primary expertise in astronomy is in visual deep sky observing. Even though my PhD is in physics, I don't know much about astrophysics. And the other thing that I have contributed is the software that got me into astronomy was an open source software. So I started contributing code back to it. And now I'm one of the key contributors to that software in the past. I mean, nowadays I don't have much time to work on it, but I still try and do something for it.
Awesome. And I think what and for anybody who knows Akash, I'm sure you already know that Akash, you have probably seen and worked with some of the biggest amateur telescopes around, being in the US, and access to some of wonderful telescopes out there, right?
True. I've been very privileged to know these people and have them as my mentors. It is really, I'm very lucky.
Awesome. So I'm sure we'll come back to that and discuss more. And really hats off to contributing back to the community. Open source, I think, is a great way, and anybody who does that is really, really appreciable. So thanks, Akash, for joining. So we'll circle back again. Vishwa, anything you want to add?
Hey, thanks, Satish. My roots from astronomy probably started during my childhood when we were staying in my native place. So my native place is kind of in very hot and dry region, and during summers we used to spend night on the terrace, sleep in the terrace, and had access to very beautiful dark skies. I mean, those were the days when there was very little light pollution and we could see a lot of stars. So probably, I could trace my origins to astronomy at that time. But after that, it's been kind of slow, and I was not actually actively involved until during my second PU days. So what happened was, one of the physics professor at a college, so he had a telescope and he had set it up just for the students. And I went there and I saw Jupiter. And he was casually showing, okay, this is that constellation, that is this constellation, and I got instantly hooked up. So how can a person simply just looking at the sky can tell so many things? I mean, I've been seeing stars from childhood, and yeah, I mean, there are patterns there. I would have studied constellations, they are there, but I really got hooked up. And later that, so once I got into work and was able to make some money, then I met Naveen, and then came to know about Bangalore Astronomical Society. That's when I bought my first telescope and have been active ever since. In addition to astronomy, I'm also an DIY nerd, electronics nerd. So a combination of astronomy and astrophotography. I mean, this was like a pair made in heaven. So I got instantly hooked up into astrophotography as well. So now I do, I mean, still I'm practicing a lot of astrophotography. Yeah, so it's been almost 10 years where I've been seriously doing astronomy. Yeah, and since and thanks to Naveen and the professor during my PU, so even I got inspired to give back to the community. So that's why I try to be more active to inspiring young people, school students to get a similar kind of opportunity like what I had. Yeah, that's something about.
Cool. That's awesome. Welcome. And completely agree with what you said there. How do we figure out so many things just by looking at stars? That's something which I've also wondered so much, and it was so intriguing initially. And it's one of the interesting things I've seen is like so much we know about the universe, at the same time it is so little. And we've been able to figure out so many things just by looking at these stars. It's pretty amazing. So yeah, welcome, Sashi. Sorry, Shashi, over to you.
So is it my turn? Shashi is speaking.
Yeah, Shashi, please go ahead.
Yeah, so I probably got exposed to astronomy in my childhood because my dad used to have a lot of books on science and astronomy lying around. So I recall reading books on planets by Patrick Moore, who was a very famous English amateur astronomer. But beyond that, I didn't do much until 3 years ago when we moved into an apartment which had some view of the sky. And it's from then on that I started looking at the stars and trying to find out more about them. And it's really from there that it all started. I just started reading something online, started to read about which scope I can buy to pick the thing up. And then I got in touch with a few members of BAS, and they helped me ramp up. So I'm still young in this field.
Awesome. So welcome again. All right, so with that, let me go ahead with the next set of questions that I had. So and now that we have heard about your journey, what would you say for, and this is an open question for the whole panel, please feel free to jump in and answer. What would be your suggestion for anybody who wants to get started into the hobby, or they have already started, they have taken the initial first few steps, but there is so many things out there to figure out. Do they do first, constellation, they look at constellations first, or do they read out the theory, or do they do astrophotography? How do they actually build the hobby, and what are the things to watch out for? What are the things to do and not to do? Um, any suggestions for the new beginners?
Okay, I would go first on this, Satish. Uh, Anybody who wants to get started, be it astronomy or any other subject for that matter, you need to know some of the things, at least the basic get started stuff. So my suggestions and recommendations would be to first take up a book in astronomy about the night sky, read it through. It will not take more than a month for you to read and then connect it with the night sky. So the best one is to take any simple astronomy night sky observing book, which has the constellations, the names of the stars, and get started with it. I still remember when I was way back in 9th standard, when I said this, when I was hooked onto the astronomy, the first book I purchased was Ian Ridford, The Night Sky. So that had only beautiful, I mean, I purchased the book not for the content, but for the pictures. So he just gave me the pictures, colorful pictures of the night sky, and then the names of the constellations so that I could star hop and identify myself. That's the first step. Once you start understanding what is a constellation, how do you identify, and the joy of identifying oneself versus somebody else showing you, there's a lot of difference. You get that interest when you identify it for the first time yourself. And then when you do this for well-known constellations, now you have the next set. The first thing that you have to do is to get hold of a local astronomy group like Bangalore Astronomical Society and meet people out there. Share the equipments that they have, join the programs. That is what I did when I had been to planetarium and I met Dr. Shailaja. The first thing she said is, for me to answer all these questions, you need to do a lot. So there is one group down ground stairs, go meet them. And I was so interested, and I joined this group ABAA way back in 1995. Okay, so the first thing is you have to join a group and get to learn from others. And then comes up when you start talking to the people, you share your thoughts, you share your ideas, you learn from the others' ideas. And Akash very interestingly said that I'm happy to have my other observers as a great mentors. And that's what you get when you join the group. You get great mentors who will take you onto the next path. How do you get your interest going on? Okay. And after that, slowly you will start realizing that the field of astronomy has so many different fields, so many different branches. So now you pick up which branch of astronomy is interesting to you. One of my branch of astronomy, which is interesting to me, is popularizing astronomy itself, because I love teaching. So popularizing astronomy is one of those things that I love the most. And that way you will find your own interested way. And then onwards, you start digging into a lot of materials in that, like books, articles, or talking to the subject matter experts in that area. Finally, if your interest is in observation, you take telescope of your own, or else you would anyway use the telescopes of the members of the group. If you're into astrophotography, start with a small tripod-based astrophotography, and eventually you know which telescope best suits your needs. Only then invest your money and get out. I would like to say this. My first equipment was just my eyes. The first optical equipment was in 1998 when I knew that my father had been to a different city, a different country, and he had a binocular. And Bangalore city was very good at that time. We could see M6, M7 through without any optical aid. And I had this binocular, which was 20x50. And that was my first equipment. I did not even purchase it. It was at home, so I just used it for astronomy. Then in 2004 or 5, that was when I purchased my first optical telescope. That was my first telescope. So though I started my astronomy in 2004 or 1994-95, my first equipment was in 2005. And today I have advanced VX mounts and computerized telescopes, 8-inch, about 3 to 4 of them. So I'm more into astrophotography as well as the observations. Yeah, that is how you go on to the path. Don't jump into buying any equipment immediately.
Awesome. True, and there are so many things involved. I had bought a telescope from a gift shop for my son, and we thought, we'll just use that and just see Saturn and see if it has really is got rings, or they just tell it just to say. And I just thought you'll just keep it, put it, see it, and then you will see. But it took like 4 or 5 months to really do that, and so many interrelated things you had to go through. It was a big learning journey by itself. So completely agree there. So I'll move on to the other panelists on that same topic. What do you think people should avoid when they first get started, when they start? Naveen, you mentioned certain things like get a book, read through it, and get a set of people you can discuss with. But what are the things they should not do, maybe?
I'll give that a shot. I think Naveen already mentioned spend your money first. That's a mistake. Money is not the major investment in this hobby. In my opinion, it is time. Even if you have the best equipment, if you don't know how to use it, and telescopes and other things are scientific equipment which take a lot of effort to learn how to even operate or even set up correctly. Like you just mentioned, it took 4 to 5 months. So I would say the best approach is to start with as little as possible. Invest your time first and effort, but not money. Money comes later. When you realize that you're past the point of recovery and you have really gotten deep into this hobby. I think that's the number one mistake, but both of you already touched on it. That's one thing.
Sure. Awesome.
And Satish, it's also a myth that many people think astronomy interest will grow to kids or to an adult only if they have a telescope. That's a myth. You don't need a telescope to get into astronomy. Okay, mere talking about the astronomical objects to somebody is also going to get you interested into astronomy. Okay.
Yeah,
Yeah.
What Naveen and Akar said. So when again, when I started with astronomy, it's not the telescope nor the any equipment that inspired me. So it's just by looking at the night sky, having access to them. That's what inspires things. So just get on, meet a local astronomy club, meet people, even if it is via online or chat or anything. Learn the skill. Yeah, then you can always invest money on that.
Sure. Sounds good. Shashi, anything you want to add?
Yeah, so I probably came from the other end of the spectrum in the sense that I straight away jumped in and bought an 18 scope. So I didn't wait around to first learn stuff. So because I thought that one will feed into the other. Spending time under skies and seeing objects might also increase my interest in actually studying more about them. So if somebody wants to do that, I think it is fine. But just a word of caution that don't purchase equipment that's too big straight away, because it's a big hassle to transport and to set the thing up. So if you purchase a small tabletop scope or even an 8-inch spread, 8-inch scope, it will still be okay. But anything beyond that, it's a big hassle to transport and to set everything up. So that's one word of caution.
Exactly. So a couple of things that have come up, right? So to summarize, looks like what anybody who's beginning could take away is don't over-index on telescopes and instruments in the beginning, and understand more about what is actually happening. It's also important to understand what is the light that somebody is looking at when they look at through the telescope. What is that exactly, and what does it mean? Why is it a big deal, and things like that. And another thing I want to just add is, I found looking from CT is actually very helpful because you don't see so many other stars, and then you can easily recognize the constellations. That way, it's a very good homework to do in the city itself before somebody goes out deep inside and observe darker skies, because there's so many stars out there. I don't know if you agree to that, but just a thought. Okay, I just wanted to open up any questions on the line on this topic as to how beginners can start, what things to do and not to do, or any other questions coming in from live streams.
Like, what are the different books we can start with?
So anyone from the panel wants to take that?
Okay, I remember there was one night sky book, and it was a pocket guide, this size. Okay, this is from Collins Gem, and I know during 1997 when we were in ABA, pretty much everybody had a book of this Collins, and that's a good book to start off. I don't know if it is still in publication, but that's a good book to start off. And there are books from Roger Friedman or Kaufman, which is like Introduction to Astronomy, Space. So I would put it this way: go to a library, search the astronomy book, read 1 or 2 paragraphs. If the author's explaining something and you're able to understand it, any random page, if you can understand it, that's a good book for you. That's how I pick up the books. So I go to this bookstore, I read 1 or 2 paragraphs. If the content is holding my attention, then yes, that's a good one.
So then let me show my favorite books. So actually, my favorite book is Edmund Mag 5 Star Atlas, but I think it is out of print. That's how I started. But Jagan Gorti from BAS showed me this amazing book. I think Jagan, I don't know who, but somebody in a BAS session pointed me to this amazing book. I purchased it. It is very good. So that's one book I can recommend. This is mostly written from the point of view of somebody who wants to be an amateur astronomer, visual observing, and just explore the night sky. It's not so much for a technical book. And the other nice book to have, as Naveen mentioned, is Friedman and Kaufman. This is a undergraduate level textbook in astronomy. The level of calculus is not significant. It's mostly algebra based. And if you don't want the math, you can just ignore the maths and just work with the concepts. So those are two books I can recommend. And then if you want to absolutely get started, P.N. Shankar was the founder of ABBA. His books are available for free in PDF format on the internet, and they are also very good starting points.
Great, thanks, Akash. So building on to that same question, hey, sorry, Vishwa, go ahead. You had something to say?
So on the contrary, so I did not read a lot of any books. So probably I can recommend this one book which I was using. So this is called Astronomy Quiz Book. So so this is structured in a way that all the information is put in a form of a question and answers. So you have specific topics and you will say, okay, what is Mercury, or what is a planet, or things like that. So I pretty much, was using this book. And later on, I did not invest in a lot of books, but most of my learnings and everything came from either Wikipedia or any online, lot of online articles through them. So yeah, so that is also another route if you're not looking for any particular hardcore books or anything.
So I want to ask a follow-up question on that, right? What role does the Messier list play? It's a very popular list. I've seen many people saying, "Hey, let's get into that. Let's observe these objects, and that will also probably a good way to also scale up in the hobby." And that goes back to the question somebody is asking on the chat as well. I think it's Nashrat, which is a very valid thing as to how do I understand what goals can I put for myself and work for that.
Okay. I was just trying to search this P.N. Shankar book. I had all these books, physical books. Akash, and the question is also very relevant. Here is a Kannada version of the book by P.N. Shankar, which is translated. And I'm sure this book is available, but it's in Kannada version. And this is the English version of this book is Nebula, Star Clusters, and Galaxies by P.N. Shankar. Okay. Here, Satish, as you rightly mentioned, in this book, you'll see that there are constellations, images, and then the positions, the relative positions of the Messier objects. Okay. Now, this is a very good starting point for people who want to get started with a small telescope and Messier objects. But where does this Messier objects thoughts come in? See, when you start observing the night sky, the first thing you see is the stars, the moon. But after that, you will start noticing some of the fascinating objects in the sky, like galaxies, clusters, group of stars, globulars, and then the nebulas. Then now you need an equipment for looking at all these things. At least a binocular is at least required. So when you start with an optical instrument like binocular or a small telescope, now you can go ahead, use this kind of a book. And what Akash said reminded me of one more thing. In Sky and Telescope website, there was a good Star Atlas PDF that was there. I hope it is still there in that website. That PDF, which had all the constellations and relative positions of the good, bright Messier objects, is a good starting point now. Why is it interesting to see the Messier objects? Pretty much it covers all varieties of objects in the night sky that can be through a small telescope. And as a visual observer, when you start, Messier is a kind of a starting point for you to start observing different types of objects in the night sky.
Thanks, Naveen. I think that does answer. So there's another question on the chat. related question. What if somebody is not really interested in looking at constellations, but they want to get more understanding about the theoretical part of astronomy, which I'm assuming is going to go more towards astrophysics and physics itself. So any books for that?
Yeah, I actually direct message to Gargi. Instead, I should have sent it publicly. But again, this book is very good for that. It's a undergraduate level textbook in this subject, so it serves as the starting point. And then as you get more familiar with the mathematics, and if you can handle more, you can go to more graduate level textbooks or even more advanced textbooks. I haven't done that. I'm actually still working through this textbook.
I think you can also see that I was also showing the same book, and this is one of the worth it books. It's called Kaufman's Universe. I have a third edition, but I think there is a fourth edition also available. Okay. And just on a lighter note, I will be sharing the list of books that I have been referring. It includes theoretical, observational, as well as optical. I mean, some kind of interesting. So I'll just show you some of the books. Like this one is called as Dynamic Universe. Okay. This talks about all the, it just talks about the universe right from solar system to the Big Bang. And see, once you start looking at it, I will share out the list of books that I have referred. I think that would be good. Just give me a moment. Okay.
Sure, Naveen, that will help, I'm sure. So let me segue into the next topic I had. I think we are at a good point where we can get into that, which is now that you figure out, maybe we have at least some idea of how to start. And you reach a point where you say, okay, now I really want to get into instruments and observe more. So what is the suggestions for beginners in terms of instruments? What kind of instrument should they go for, and how do they avoid the ones that should be avoided?
I am just thinking of a wild rule, okay? Unless it is binocular, if you want to use a telescope, if the telescope is not as big as your arm length, then it is not worth it to begin with. That means that get rid of all the show pieces and then the advertisements, which has a big boxes. I think you should just avoid those small ones. The first thing is 99% of the times to start with, you don't need a telescope. When you need a telescope, here is a recommendation: go with a minimum of 6-inch telescope. That will keep you busy for at least 1 to 2 years. And if you are a adult, more than 18 years or 20 years college student, then you should start with 8-inch telescope. That is what I would suggest as a beginner's one. And do not get started with go-to telescopes. Use a Dobsonian telescopes. Dobsonian 6-inch or Dobsonian 8-inch is really good to start with. And a star atlas of 8th magnitude should be good enough reference for you to get along. Do not buy telescopes which are like 3,000, 5,000, 10,000. They are not worth it. You will just keep it as a model in your room. That's it. Binoculars are a must for every observer. I would say the moment you have a telescope, buy a 10x50 binocular, and that binocular is going to be helpful for you to look at the wider field of view and try to understand what you're observing in the night sky. That's a good one. 10x50 binocular with good optical quality mirrors, optics with a quality very high is a good one to start with. That's from my side.
So adding on to Naveen's point, so even buying a much bigger telescope like 10-inch, 14-inch, or even way beyond that does not also make sense, as again Shashi indicated earlier. So the right kind of telescope is something that you are comfortable to take it to a dark sky, because the best aperture is the fuel that you put in your vehicle to carry the telescope and you see through it to the heavens. Yeah, that's one point that I want to add.
Akarish or Shashi, anything you want to add?
Yeah, I just want to add something. So if somebody is looking for a comprehensive book on all the kinds of equipments that are available for visual astronomers who are just starting or who are also experienced, there is a book called Ware by Philip Harrington. So you can pick that book up. He walks you through all the kinds of uh, instruments that you can purchase, and he has some questions at the back of every chapter that actually gauges your interest in the field and your background in the field, and then he makes some recommendations based on that. So that will be really useful.
Cool. So there is one more.
So, sorry, I just wanted to say that Naveen pretty much said everything that I wanted to say on this front. That is, you should not start with a telescope that is really small. If you choose to start with a telescope, otherwise the preferred route is to get a binocular. He already mentioned that.
Sure, Akash, definitely. So one associated question I have, and this is a common theme I see, which comes up again and again, right? Which is around kids. So many times there is this question slash this thing about, hey, my kids are very interested, so what do we do? So what kind of telescope should I buy for a kid, or a binoculars? I just wanted to see what you guys think. Is it something that, let's say if there is a kid under 10, is it a good idea to start with uh, instruments?
Okay, here is the box that I would like to show you. If you see any of this kind of small boxes, you can see this kind of boxes and telescopes. It says 10x, 100x magnification. Do not buy these things. This is an example of do not buy. Okay. Uh, it's better to get started with a small binocular. 10x50 is a good one to start with. And this is at the extreme end when I have met a lot of parents who are like, no, sir, you don't understand. My kid wants a telescope. If I don't give them a telescope, they'll not get interested. For such parents, I would recommend them to take their kids to a local group or to a star party, make them look through the bigger telescopes, let them enjoy through the bigger telescope. And in the worst case, you need to put the money saying that this is wasted. That's the context that you have. And buy at least a 4-inch telescope. A 4-inch could be a good starting point for a lower primary kids. Anything which is less than, anybody who is less than 8 years of age, I would suggest that you avoid a telescope for such age group. Okay. The next one is a 4-inch is a good one to start for high school students. But after that, immediately you jump to 6 to 8-inch telescopes. Okay, Dobsonian, preferably a Dobsonian. What else should I say for that? Here is a very interesting one for those parents who are looking at the telescope buying, especially. If you give a low quality optics telescope to your kids, your interest is to bring interest to your kid, but unknowingly you're actually doing the other way around, reverse. If you give a low optics quality, a low quality telescope to your kid, they are not going to look at moon, planets, at the pictures that you show it on the box. So they get more distracted that the telescope is not showing me what I wanted to see. And they may lose interest in astronomy. Their losing of interest in astronomy is purely because of your choice of low grade telescopes, cheaper telescopes. So avoid them. It is better to avoid them rather than gift them those small things. Okay. Starting with 4-inch is a good one. High optics, quality of the optics should be good. That means it may cost you anywhere between 25, 30,000 or more as well. But then the optics quality should be really good. So focus on the optical quality when you purchase a smaller telescope. By the way, even Galileo used 2-inch, 3-inch telescope, but the optical quality was extremely good. One of my friend had a 2-inch, 2.5-inch refractor, and I was stunned to see the image of Jupiter, Saturn, the rings of Saturn and Cassini division, and that blew me off. But the difference was the optical quality, and that telescope costs some 60,000 or something like that. So it's the optical quality if you want to go with a smaller aperture size.
And refractors are anyway notoriously expensive, but I think come with good quality. So, and how good is it to maybe just, especially for kids, just to be able to identify constellations? I think that itself will be such an exploration for kids, especially. and its sense of achievement, because at least for me it was, once I was able to identify constellations fairly well, I think it gives a good sense of achievement also, right?
Adding to what Naveen has mentioned, this is exactly what happens when you buy any cheap kind of telescope and you end up not using that. So probably even I can relate to it, because I had bought a very 5-inch telescope, but since I was into DIY and everything, somehow I was able to sustain. Probably I could say the 5-inch telescope is one of the reasons why I was not able to get into the visual astronomy, because I was fed up with looking at the clusters and everything and seeing them as a very faint objects. And looking at the pictures of the Hubble and other astrophotographers, so I directly jumped into that and started going towards that. But again, at some point of time, after interacting with Akash and others, there is a lot more to explore, even with a smaller telescope. So yeah, there is a chance that one day I might even switch back to visual astronomy, things like that. So yeah, so don't make a mistake of buying any cheap telescope and everything. So you will actually end up killing that passion for astronomy. So my best suggestion will be take them to star parties. So probably is so 10 or 12 years kids, so they'll be very active during the star parties. So we'll have a lot of telescopes, so they can look through that, so they can actually judge what exactly can be seen through the telescope. Yeah, and when they are ready, yes, they will know what exactly to buy.
True. And I think an experience with Star Party also gives that first-hand experience about how it's not all very easy as well. You need to go and look through the telescopes, stay awake, but that the real feel comes in, and you see the entire gamut of things, which is, I think, a good experience. Uh, okay, so before we move on, I think I just wanted to touch upon two more things on instruments before we go to the next topic. So how do we, how can beginners or anyone, right, calculate magnification quickly, and what magnification is after which you should not go for buying or using an instrument? So how to calculate, as well as what is the limit you think we should look at? And also associated question, what is this L5 L6 kind of configurations that we have, and how do people make a choice on that? So anybody wants to take that? Akarsh, Shashi, Vishwa, Naveen?
Yeah, I can take it up. So accordingly, so the thumb rule is that the maximum magnification that any scope can support is about 40x per inch of aperture. So that is a rough thumb rule, but people break it all the time. They go to up to 50 or even 60x. But the thumb rule that I've often read is do not exceed 40x per inch of aperture, else you just end up magnifying the area disk and not the actual object.
And you say per inch, Shashi, what do you mean there?
Per inch of aperture. So if it is an 8-inch, you must not you must not exceed about 320x.
Got it. That's interesting.
Satish, without getting into the lot of mathematical calculations or anything, so what I say, I would like to answer this in a slightly different way. So telescope has two purposes. So one is magnification. Of course, it makes farther things appear closer. And second thing, it's light collecting ability. Lot of deep sky objects like Orion Nebula, Andromeda Galaxy, they don't need magnification. So what they need, so they are faint. So obviously that's the reason why we can't see doing with a bare eyes. So what we need in addition to the magnification is its light collecting ability. So one of few of the best views of Orion Nebula or anything, I have seen that at a very low magnification in my telescope. Uh, so don't simply fall into that magnification factor. If any boxes or anything such as like 400 or 500, yeah, you should go and buy them. Yeah, but when you're observing planets, yes, you will require magnification, because you want to see more details in that. And since these are basically the bright objects, you don't need that kind of a light collecting ability, but yeah, you would need magnification for that. Yeah. So yeah.
Yeah. So basically, you can consider like this: magnification is, I think Akash has already sent the formula. the focal length of the objective divided by the focal length of the eyepiece. Now, the focal length of the primary objective is going to be fixed. Like, for example, you buy a 8-inch f5, 8-inch and f5 means 1000mm focal length. That is fixed. The only way you can alter the magnification is by changing the eyepiece. That means you can use different eyepieces to change the magnification. So when people talk about what is the magnification of a telescope, that's a wrong comment, wrong statement. There is no magnification for a telescope. There is a magnification for a combination of the primary and the secondary eyepiece. I mean, the eyepiece that you use, that combination will give you a magnification. Now, if the thumb rule, as Shashi was saying, that's a nice one. And the focus is this. Just imagine you have a camera, and in that camera, if you have a 2-megapixel camera and you want to zoom in a lot, what happens? The data that the camera has captured is very less. With that less data, if you want to zoom in a lot digitally, you lose the quality of the image. Exactly that way, when you have a smaller telescope and you start magnifying it using lower focal length, like 4 mm, 2 mm, or 8 mm, 9 mm eyepieces, then what happens is the clarity, the light gets so much distributed, and you will not be able to observe and enjoy the object, look through the object. Okay, basically observe the object. So there is a limit to which you can, two things, one, magnify and also resolve. So you need to, if you want higher magnification, go with a bigger aperture, so that it is like using a 24-megapixel camera. Even though with a digital zoom in, you can still have the better quality or a clarity, a resolution. Okay. Galaxies don't need too much of magnification. If you want to observe a few craters on the moon, you need magnification. So moon being a big object, bright object in the sky, the brightness, you can magnify it more. So that is how small telescopes with higher magnification on moon will give you good result. But the same small telescopes, higher magnification for galaxies or nebulas will give you very bad results. So magnification is something that you should not always look for. You should look for the focal length. And there is one more interesting point that I want to add. The bigger the focal length, it is good for planetary. That means if you have 2000mm focal length of a primary, then it is good for planetary and bright objects. The shorter the focal length, it is good for deep sky objects. So somewhere f5, f8, somewhere around that range is a combination of both. Like it can be used as a mid range for both this areas. So that is what you need to look at. Yes, Akash.
So did you mean that you said you meant, did you mean that you should look for aperture and not focal length, or did you mean focal length?
The first thing is, if you want magnification, then you need to look for aperture.
Ah, okay.
After aperture, you need to look for the focal length.
Makes sense. Perfect.
If you have let's assume this, you have a 20-inch telescope. Now, 20-inch telescope does not mean that it is good for deep sky. If the aperture is f10, I mean, that is good for planetary. You will see beautiful images of planetary. But the same 20-inch telescope, if it has got f4, f3.8, then that is good for your deep sky. And the combination of this, along with the eyepieces, will give you a better resolution and magnification, because the amount of light collected by this focal length, I mean, the amount of light that you have at the focus is so much that even if you magnify, it will be good enough for you to resolve the things. So first is aperture, then the focal length, and then the magnification comes in. So all these three combination goes into what you want to observe. Okay, I'll give you another indication. I have a telescope which is 8-inch f5, and Saturn was beautiful. When I use this 2-inch telescope and my friend 2-inch telescope, and I looked at Saturn, I was stunned because the 2-inch telescope showed Saturn much better than my 8-inch telescope, because that aperture was extremely big. It has I don't remember the aperture, but it was bigger. So it had given us better results. Okay, that is what I meant, Akash.
Great. I think those were some very interesting points. Any questions on the phone or on the live feed on instruments before we move on to the next topic? So there are a lot of questions on binoculars. I think we have already seen that. So we'll probably publish a entire catalog. I mean, Sudhansha's put a list of objects which are good to see via binoculars. We'll share that on the Telegram group. If time permits, we'll come back and maybe do a screen share and go through it. But are there any other questions on instruments at the moment?
Okay. I think Narsat, the question on the optical quality. So how do you judge the optical quality? Okay. The judgment of the optical quality is one. The brand of the telescope model or the instrument that you're buying should be well recognized and good at optical instruments. Okay. In such cases, like we have good brands with the Celestron Mead, the Skywatcher. There are a lot of brands in which you get these optics made. The second one is when you look through the telescope. That's why when you look through the telescope and do an actual test, there should not be any aberrations, chromatic aberrations, be it binocular or the telescope. There should not be any chromatic aberrations. This chromatic aberrations is going to spoil you. Even moon will look colorful. You will look at moon and it will feel like you're looking at a rainbow moon. I don't know if people who have small telescopes and you will notice that your telescope is showing a rainbow moon. It means it is a lower quality optics. So, Nasrat, the only way that you have to know the quality of the telescope is don't buy the telescope. Look at the telescope that others have used. Look at the quality of that telescope or the optics, and then decide, okay, I have seen, let's say, Celestron 1 model. I have liked this. The quality is good. I will purchase a similar model. You should go with that kind of thing.
Yeah, so adding to what Naveen said, so it's the reviews of other users and other astronomers. So you can probably check some posts or some equipment discussions that happen on Cloudy Nights or any other popular astronomy forum. So in addition, so when you're choosing refractors, so there is something called as doublet and triplet. So triplets obviously will give you a much better optical quality because they have 3 lenses and then they correct for all kind of spherical aberrations and everything. Yeah, so best way is, you have to know a little bit about the kind of instrument. So yeah, if it is a reflector, so what kind of mirror it is, whether it is spherical mirror or parabolic mirror, the F ratio, those things. Yeah, so best way it is, as Naveen mentioned, see the kind of reviews, what other astronomers say about the telescope. Yeah, then you know what exactly you're buying.
All right, great. So if there are no further questions, I would probably like to then move to the next topic, which was to do with a little bit on the solar system. So there were a couple of questions that were submitted. One of the most interesting ones being about the mystery of Planet X. So what is Planet X, and what do we know about it, and what does this mean?
Okay, let me take a lead on this. So, probably historically, I mean, if you see, only probably you can see planets only till Saturn with your bare naked eye. But then they discovered Uranus, then they discovered Neptune, and then discovered Pluto as and when the advancements of science and technology happened. So yeah, so Uranus was discovered because of the orbital perturbations of Saturn, and then they found out, okay, there might be a planet over there, and then they found that, okay, even the calculations for Uranus is not matching, then there should be a planet there. And then in recent times, with the advent of telescope, they found out Pluto. So what if there is another planet beyond that? So now with the lot of advancements in technology, in optical data processing and many other things, so we are able to see so many objects beyond Pluto. So what we did was we categorized them as a Kuiper belt objects. So and recently even I came across an article. They say that they are still not able to explain some of the orbital characteristics of the Kuiper belt objects. So they might be an planet beyond that. So I mean, it's not that it is physically there, but the only way right now with the data what they have, they can only explain that if there is an object of certain mass over there. But it has not been observed right now with the current technology. Yeah, who knows, when we have much better technology in the future, we may able to discover the object that exactly fits the scientific model that has been developed. So right now, yeah, there is nothing like Planet X, but it is in the theory as a theory to explain some of the permutations of capable objects. But yeah, we have to wait and watch.
Cool. So it's a theoretical prediction as of now, and we understand that because by looking at the orbits of some of the other planets beyond Neptune and looking at the way all the other orbits are around that area, we theoretically feel there should be another object to counterbalance that. That's what I'm taking away right from here.
True. So basically, every planet beyond the Jupiter and Saturn, we noticed that the orbital parameters were not as predictable. So there was some perturbations. There were some elongations. Now eccentricity. Is it purely because of the sun and other planets in the solar system, or is there anything beyond our observations? That is what is X. So I go with this. Mathematicians always call something that is unknown as X. Find X, 2X equals. So it could be like that planet X. So planet X means we are yet to find a planet which will help us solve this problem where things are not behaving the way they have to behave. So that could be the origin.
And another thing that is very common when it comes to solar system is about this Pluto. And there is a question as well. Somebody submitted about on what basis was Pluto branded that it's not a planet anymore.
Okay, let me take up this question. In fact, Pluto is a very interesting object in the solar system. One, it is the most distant object that at least we knew for the last 2-3 decades. And over a period of time, because of the technology and the telescopes, we are able to find more objects beyond Pluto. So till the Pluto was discovered, in fact, Pluto was discovered in the 19th century, and it was also discarded as a planet in the 19th century and early 20th century itself. So it did not even complete one round around the sun before it was demoted from the planet status. Why did this happen? Like Vishwa mentioned, what we had is with the technology and the telescopes coming into picture, bigger aperture telescopes and higher resolutions, we could go deeper into the space for resolving objects and smaller objects. Scientists and observers, we started finding out that there are a lot more objects beyond Neptune, and they are in size comparable with Pluto. Now the question is, if the objects, like said now, they are comparable with the size of Pluto, should we go ahead and just add those lists into the planets list? If we started adding all those new objects that were found as planets, then we could have today approximately 14-15 planets. Okay. Now, there was a condition put up. From the history, planet always meant the word wanderers in the night sky. Means it was just on observationally, planets just move in the night sky with the fixed star patterns. So anything that moves in the background of a star got this word planet to begin with. Later, as we started finding more objects, so initially we had only about 5 physical planets like Mercury, Venus, Mars, Jupiter, Saturn, which was visible apart from the Earth. So these are the 5 planets we could see. But later we got Uranus, Neptune, and then the Pluto was there. And discovery of Neptune was because of the disturbances in the Uranus orbit. The discovery of Pluto was because of the Neptune's orbit. Similarly, there are other objects that are found in the recent times. Now, do we want to have n number of planets, or should we go back and question this word? What do you mean by planets? What is the definition for a planet? And that is what IAU did, International Astronomical Union did. They just went back and changed or defined it. They did not actually change, they just defined the meaning of the word planet. And when they did that definition of a planet, they gave 3 conditions as a planet. Any body, any astronomical body that satisfies these 3 conditions, it will be called as a planet, as simple as that. What are the 3 conditions they put up? The first one is it has to be sufficiently big and it should be going around a star, obviously. So a planet is a heavenly body which goes around a star. It's our sun now. The second one, it should be sufficiently big. Why should it be sufficiently big? According to our physics, any object which is sufficiently big will form a spherical shape. So the spherical shape is nothing but the most stable shape for, I mean, the maximum volume with the lesser area, like it's a most stable shape. So planets will eventually have to be spherical in shape. So you have a spherical body going around the star. The second one is it should be so big that it should absorb or get rid of all the materials that are in its orbit around the star, basically a planet. It should be cleaning up all the neighborhood. And this is one of the most confusing one. What do you mean by clearing the neighborhood? Meaning no bigger object, I mean relatively big sized object should be sharing the same orbit of this identified object. For example, if you consider Jupiter, Jupiter should clean up its environment, its orbit around the sun, and there should not be any considerable bigger size object in its orbit around the sun. So now Jupiter does not have, so it's a planet. Next, it should not intersect with any other planet. If it intersects, it means it is not cleared it. So Jupiter does not intersect any other planets, any other objects, so it is planet. Next, go to Saturn. It is another planet. Uranus, Neptune, planet. But the moment you put Neptune into a planet category, that it has cleared all its orbit, now the condition comes up. If Neptune is clearing, there is a Pluto which is cutting its orbit. Okay, for approximately 1979 to 1999, Pluto was much nearer to Earth or to Sun than the planet Neptune. But then it cut the orbit, but it was in a different plane. And since you consider Neptune as a planet, Pluto is not considered as a planet because there are other objects in that zone. Okay, and there was an intersecting. So if I consider Neptune as a planet, applying the same formula for Pluto, Pluto cannot be a planet because it is not clearing its orbit. And that is how Pluto was removed. A definition was given to planet. So, I mean, in astronomical terms, there is nothing changed. Pluto is still there. It is only our definition has changed. That's it. So I'll give you an example. You have a polarity in the magnet, you have a polarity in the electricity. I mean, there is no standard. We made it as positive, we made it as negative. We said north and south, that is all. Tomorrow, if somebody goes and says, okay, we'll invert this into different names or different definition, the word is not going to change. We are just going to change the formula, that's it. Exactly that way, Pluto's status was removed from planet. Yes, sir.
Cool. Thanks, Naveen. I think that is a very good explanation, and some of the points I didn't know myself. So yeah, great. Thanks for that. I actually want to, given that we are like 150, I was thinking to open up for the line to see if we have any questions from people. But sorry, I heard somebody saying something.
No, Satish, I was just trying to continue on one more very interesting point. Because we removed Pluto from its status as a planet, a new definition was added. If any of the above 3 rules were broken, then the object could get a status of a dwarf planet. Dwarf planet means it did not satisfy one of these rules, or it did not finish off the neighborhood clearing activity. So it is still in a dwarf state. Now, The moment you define the dwarf state, what happened is, you know, the asteroid belt had the big Sirius as one of the big asteroid. Now, when we were in school, we studied that there were 4 big asteroids: Ceres, Juno, Vesta, and Callisto. Okay, and not Callisto. Ceres, Juno, Vesta. Was it Callisto? I think so.
It's
No,
Pallas.
Callisto, Pallas. Sorry, Callisto is the Jupiter's moon. Sorry. Oh, Pallas. Now, out of these, Ceres has now become the dwarf planet by definition. So it is no more an asteroid. It is now by definition a dwarf planet. And moon of Pluto, which is Charon, that has become a dwarf planet also. So by definition, we got new objects into dwarf state, and Pluto was removed from the planet. So it is just evolving science, that's it. So you should not, or we should not have any emotional attachment to it. Okay.
Absolutely. Absolutely. And I think a lot of science also needs conventions, and without conventions, of course, you don't have a baseline to actually construct other things on top of it. And a lot of things are conventions in science. So yeah, I think that helps. That summary is good, Naveen. So yeah, so let's open the floor and see if there are any questions. There are actually a lot of topics we can go through, and there are many other questions that have been submitted, but I wanted to give a chance to people on the phone to see if there are any immediate questions, any topic actually.
Okay, I will pick up one of the questions from Mukesh, who is asking for all open clusters are spread across the sky. Is there any preferential path or patch? Uh, for that, Mukesh, here is you need to just understand a little background around what is this open clusters. Open clusters are formed in bunch. Why? Because the picture that you see in the background here for me, that's a Orion Nebula. That's a place where stars are being formed, and the nebula will now get sufficient mass to form the stars and eventually create an open cluster. So that's the first stage of how the stars are born. So this nebula that you see here, Orion Nebula, over a period of few million years, will have X number of stars. At least with the data that I remember, Orion Nebula has approximately 1,500 solar masses equivalent mass there. Okay, so even if I consider as sun, 1 solar masses kind of stars are being formed, probably after a few million years, you will find 1,500 stars in this region. That becomes a open cluster. Now, open cluster is a relatively young group of stars. Their age is very young. They are very new stars. They are still on the main sequence, very new stars. Now, the 2 conditions that I was trying to tell you is, in the galaxy, if you look at it, where does the new star get born? They're always on the arms of the spiral galaxy. The arms of the galaxy is where the stars are formed. That is where the hydrogen and helium, the necessary interstellar medium is, okay, or the gases. Now, the arms of the galaxies will give rise to the nebulas, and then that give rise to your clusters, and they are relatively new. And that is where you will find that around the disk of the arm, you will always find open clusters. Now, in the same way, there are globular clusters. The globular clusters are like mini galaxies, or there is a big question still not answered, whether globular clusters came first or a galaxy came first, or was it at the same age? So globular clusters are small clusters of stars, typically around 1 lakh stars to 10 lakh stars within a small range. Those are found away from the disk. Now, if you look at the open clusters, they're on the arm, and globular clusters are usually away from the arm. And that's a very interesting one. So if you have Akash and Vishwanath, I'm sure they will agree with me. You just take a telescope or any equipment, you see a Milky Way arm in Orion, Cassiopeia, Cygnus, Perseus arm. You just take your binocular or telescope. You don't need to know anything. Just keep the telescope, keep moving the telescope in that arm. You will see a lot of clusters there, because that is rich of stars, the new stars that's been born. And that's the reason why it is only at the disk level. I hope that answers.
Sure, it does. So, Akash, going to you, and I'll build up on a point that Naveen brought up, right? So when if you, given that you have done a lot of deep sky observation, right? What are some of the most interesting clusters you have seen on the arms, like Naveen was mentioning? Any your personal favorites? Of course, not that is visible only via 40-inch scopes, but more accessible to common people. What would you say?
So I must confess that I am not a fan of open clusters. So I got tired of them very quickly. But I will say I will tell my favorites. So of course I like Pleiades. Of course I like Beehive cluster. But I think my favorites are going to be double cluster is a good one. There is M35. I like M35, which is in Gemini. It's sometimes visible to the naked eye. And there is a very nice cluster near, there's another open cluster very close to M35. It's an NGC object. I don't remember the number. That pair is really nice. M46 is very interesting to me because of the planetary nebula that's in it. I can't remember if it's just line of sight or if it's actually a member. And M52 is a very nice cluster in Cassiopeia. And I'd say M48. I remember good things about M48. And oh yes, M93. These are my favorites. And the 37, the 37 cluster. Yes.
Oh, bye. I am a big fan of open clusters. Okay. And
Hey, Akash, can I request you to maybe later on share that list of numbers that you just mentioned? I think it'll be good for people to explore.
Sure.
All right, great.
Here, I am a big fan of open clusters, Satish. And why is that? Because when you're educating people, showing them open clusters is really interesting. They'll see a lot of stars in the field of view. Some of my favorite open clusters are already, Akash has been saying, the M35 is beautiful. M41, which is M35 is at the leg of Gemini, that's towards the northern side. Okay, you should watch if you have a binocular or a telescope. And then M41, which is below the Sirius star, brightest star, that is very good. Sagittarius has beautiful open clusters, and the Scorpio has beautiful open clusters, M6, M7. Auriga has M35, M36, M37. No, 36, 37, 38. Those are very good ones. So each of these open clusters have different shapes, different count of stars. So you get fascinated that the stars gets formed, but there are different number of stars being formed. And that puts into a question like, I mean, how big could the original nebulosity be? Yeah, that is something that I like. If you have a small telescope with low magnification, don't forget to watch this double cluster in Perseus. Perseus, what is this? Was it Perseus?
Yes.
Yeah, double cluster.
Yes.
That's a beautiful one. Okay.
Yeah, adding to Naveen's point, right? So one more good thing about clusters is, so almost every object in the night sky, when you look through telescope or binocular, everything looks black and white. Only with stars you can make out some colors to that. So, and yeah, when you are looking at some of these clusters, like the cluster at the center of Rosette Nebula, so one of the stars is in yellow and other stars in blue color. So this is something, and there's again the jewel box cluster somewhere in Scorpio. That again you will have, I mean, you'll be able to make out the color differences in the star. So probably that is one of the colorful objects I can tell in the night sky. So these open clusters are.
If you just look at just the cluster, then Omega Centauri, that's the best cluster you can see. It's a globular cluster. I mean, it will fill your field of view. It's beautiful. Yeah.
And is it that Omega Centauri, I remember so distinctly looking at through a binoculars, and the binoculars, it was just amazing. So is it a better binocular object, or it looks great on the telescope also?
Now this is what I was trying to say, Satish. If you have a low f ratio, like a telescope which is f5, f4, and you have a low magnification, focal length is less and lower magnification, Omega Centaurus is awesome. Okay, so even with 8-inch telescope, it will look good. Basically, what is the difference between binocular and a telescope now? A bigger telescope, you can have a resolution of this cluster. It just resolves each star. And Vishwa was talking about the color of a star. People with 6-inch telescope with low magnification can see beautiful golden yellow stars in Omega Centauri. And that's a breathtaking. And I remember in Akar's 17-inch telescope, when we had been to one of our observations, Omega Centauri was almost like a 3D image in the eye field, in the observation session. It was almost like a 3D. There were some stars which was popping out, some stars which was the depth, and we could see that effect. That's one beautiful cluster.
So I want to
agree.
Big aperture telescopes, the more, they are able to resolve globular clusters. Now, open clusters, almost every telescope can resolve them. But once you get into 16-inch, 17-inch range, you can start resolving many globular clusters, and then they are a really wonderful sight to look at through very big telescopes. So I think for an object like Omega Centauri, 16-inch plus aperture is actually really nice, but you can also see it with naked eye. It's just a different experience at different aperture levels.
Okay, so that is really great. A lot of interesting points and interesting discussions. We are at 2 o'clock now, so just wanted to check again if anybody has any questions from any other topic related to astronomy.
Satish, there is a question from YouTube.
Yeah, go ahead, Sudhanshu.
The question is, how useful are filters to view Mars on my 50 AZ telescope? Currently, I see Mars as a red spot without any details. This is a question from Raghu from YouTube.
So I am not a planetary observer, so if anyone else is better about this, they can take it up. But my experience with Mars is that Mars is extremely hard to see in great detail because of various factors. First of all, you need the atmosphere to be very stable. You need very good seeing, as they would call it. Second, you need your optical quality of your telescope and its collimation should be extremely good. And third, you should be able to put very high power on the telescope. So ideally, you want a bigger aperture telescope with sharp optics. And it at 50 is 50 AZ a 50 millimeter telescope? That is what is it? About 2 inches. If that is the case, then definitely I don't think you will be able to see much more than a red spot for Mars. If you are looking at a 4-inch or a 6-inch telescope, then you have to place it outside in the environment for about half an hour. You don't need much more than that in Bangalore, but it has to cool down to the environment. Mars should be very high up in the sky. Sorry, I had a small problem. Mars should be very high up in the sky, and you will need to have excellent optics and use your highest power eyepieces and track either manually or automatically to do it. Mars is a tough object to observe, and I personally have never used those filters, so I don't know how useful they are. But seeing Mars as more than a red spot in your telescope is pretty challenging. That being said, Jupiter and Saturn are much easier targets, and once you have first, my recommendation is, if you are a beginner, first try and observe detail in Jupiter and Saturn, and then you will start observing. You'll be able to better assess the quality of your equipment and so on, and see what are its limitations and so on, and then assess what you can hope to see with Mars. Mars is much harder. The final thing I want to say on this topic is try to observe Mars at its closest approach, which I think happens once in 2 years. I mean, recently we had a very close approach. That's not going to happen for a while, but once in 2 years, you have a fairly close approach, and that's when it's best observed.
When it comes to the 50 AZ, There are a couple of things that one has to understand, especially Raghu. 50-inch is a refractor telescope, a lower end telescope, and it is an alt azimuth. So the moment you try to focus on Mars and try to magnify it to see the object, it's already out of your field. And since it is an AZ telescope, you need to again align it. Now, the moment you have a higher magnification to see more details, the object does not stay at the center. That is where you need a go-to telescope, which will keep the object right at the center and track it. And you can go with a higher magnification. So if you are able to see that Mars is red in color, unless you magnify it and it remains in the center, the filters that you are planning or you are looking at will not help you. Yes, if you have a 8-inch or 10-inch telescope, and then you can put that Mars object in the center of the field, and you use like 4 mm eyepiece, then you need then the filters, especially the red filters, to just enhance your red color on the Mars, would help you cut off some unwanted light. So only when the object is pretty big enough, that is when you will be able to see good features with the filters. Otherwise, it is not useful. In fact, yesterday I and Vishwanath, we were having a lot of discussions because my 6-inch go-to telescope, I am able to keep Mars at the center, but there is some collimation error and I am unable to see the features of Mars. So just to give you a comparison, on my 6-inch telescope with the lower magnification, Mars looks very similar to the way you would look at Jupiter in your 50 AZ telescope. So that is how Mars was, the size of Jupiter in your telescope was the size of Mars in my telescope. And it was not showing me any features. I tried using the filters as well. I had filters, I had tried it. Filters don't add value unless you have a bigger size. A lot more light to it. And that is where Akash was talking about tracking is very important and aperture size matters.
Great. Thanks, Naveen. Any other questions we have?
Sir, how does the naming of the galaxies go in, or a star or something?
I can take this question if necessary. So when it comes to naming of astronomical objects, there are just too many to give every one of them names. So the few big and bright and most recognizable ones, they have names. Like, for example, Ptolemy's cluster has the name Ptolemy's cluster because I think it was first described by Ptolemy. Similarly, there is butterfly cluster, which kind of looks like a butterfly. It's a bright one, so it has a name. Similarly, the bright stars in the constellations, they have names. But after a certain point, there are too many things to name, and so you have to give them some sort of numbering system so that you can keep track of which ones they are. So the first such catalog is of deep sky objects. By that we mean galaxies, open clusters, nebulae, and such things. The first such catalog is the Messier Catalog, the M stuff from 1 to 110. That was produced by a Frenchman named Messier in, I think, in the 1700s. After that, many other catalogs have come. For example, the New General Catalog, NGC, Index Catalog, IC, and so on and so on and so forth. There is no end to catalogs. Sometimes there are professional astronomers who find a certain object so interesting and so unique that they give them a name. For example, one that comes to mind is Teacup AGN. This is some distant bright galaxy, active galaxy that has some special feature that makes it look like a teacup. It's very interesting to professional astronomers for other reasons, so they have given it that name. But names are rare. This is how the numbering works. And let me also make one more point on this front. Most of the star names we know are Arabic names. When we say nowadays, I mean, I think there is more a Western pronunciation to it, like Al-Nitak or whatever. Whereas really those are Arabic names that were found by the first Arabian astronomers. and some of them have Greek names. These are for the stars. For the objects, it's just modern English names, whenever we find them interesting. I hope that answers the question.
Sure, I would like to add a few more things here. When you, Rajpal, when you try to find, when somebody finds a star, when somebody finds a night sky object or an object in the space, if it is big object, pretty much you get to name it. That is how the standard, like, let's assume that you find a new planet, you can, I mean, big planet size object, you get to name it. Similarly, different objects has different naming conventions given to it. So for example, if you find a comet, you get to name it. So every comet has two names. One, the popular name, which is through the name of the finder. The second one is a designation, like when was it found, which month, how, which, like for example, before 15th of every month, after 15th of every month. If you find it before 15th, it gets an alphabetical letter from A to Z, and the second letter is again with a C name as a, what do you call, repeated orbit. So you have different naming conventions for different objects. When it comes to stars, there are so many stars, they can't give you a name to a star, except the big ones like Mag 4, Mag 5 stars, which are already been given the names. So now if you have to find a new Mag 4, Mag 5 or 2 star, it has to be a supernova. So even supernova, which is as bright as -1, -2, that also gets a designation as supernova with the latitude longitude. Quasar gets a latitude, right, RA deck position. Okay, so the supernova, quasars, all these deep sky galaxies, any new galaxy you find, it gets a name associated with its coordinates. So that's the easiest way to name it now onwards. So you don't get to name it unless it is a big object. Asteroid, you can donate a name, but then you can put a name, but asteroids also have a designated number to it. So naming an object in the night sky, there are certain rules given by IAU. And is the first person who finds it gets a privilege to name it. Otherwise, the second person does not. I hope that helps, Rajpal.
I just wanted to ask, you say you find some new object. How do you know that the object is already discovered by people or it is something new?
That is where Akash was talking about the known catalog of objects. So it is like this. Let's assume that you have created a new word and that does not exist in the dictionary. Now, what can you do? You can just go ahead and add it to the dictionary and then say, okay, Rajpal has found this new word. So even our dictionary gets added with new words every year, right? There are new words that gets formed. Exactly that way. The catalogs will have some known stars and objects in the sky, be it binary stars, clusters, globulars, any object. Now, any new thing that you find, it will be compared with existing stuff. That is why when you find any new object, even with an asteroid, here is a step that I'll just give you an example with asteroid and comet. The same thing applies for others. Let's assume that you're looking through a telescope and you found one object in a place that does not reflected on your star chart, something like this. So here is a star chart, example of a star chart, and it is not in the star chart. That means in the known database. Now, what you do, you go ahead and compare it with all the known objects, known catalogs. You have to do that comparison. And then you have to prove that this object does not exist in any of the catalogs, any of the places. And that coordinate, you have to send it to IAU, saying that I observed from this location. This is the proof of my observation, maybe a photograph. Usually it is a photograph, the coordinates, the magnitude, relative positions, and how you arrived at this. Basically checking at all the other catalogs that it does not show you, and then go to the next step saying that, okay, a new object has been identified. What IAU will do is they will also do the same repeated step, saying that, okay, have you checked with all the catalogs, much deeper objects? If it is new object, they will designate a number to it and then say, yes, you have found a new object in the sky. All these things have to go through. So for this, what many people have done is they have automated the whole process. So what they do, they take a picture, they will have a processing instrument, computerized automation, wherein it will search through all the existing database and then figure out, okay, here is my suspect 1, here is my suspect 2. For all that matter, a shooting star could be there, an asteroid, a known asteroid could be in the place, because a known asteroid is moving in the field. So you will say that, oh, I found something that is in the field, but it is actually a known asteroid. So they will have to check with asteroid list, the orbits. So there's a lot of background work going on. And that is why the first person who can do all these things and report to it, to IAU, gets to name it.
Okay.
Very fascinating. And I'm sure that's where a lot of machine learning also is getting used in some of these areas, I believe. Yeah. Sorry, there was one more question.
Yeah.
I have one more question. See, they have found out this farthest galaxy, that is some GNZ something 13.2 million years, which is 13.2 million years back it was found, right? So now what is my question is here, now they say it is either it does not exist or it has moved further away from us. Okay, but how are these people proving that this light what was captured by Hubble Space Telescope, that this galaxy existed and now it may exist or it may not exist or it has gone much further?
Okay. You want me to take up this one? Anybody else wants to answer, or?
Actually, what I would suggest is, because this will get into cosmology very quickly. Rajma, if you don't mind, can I hold on to that question? Maybe we'll come back. And there is another question that has been waiting for some time, which is a more easier and defined question. But we'll come back to this one because this is an interesting topic. Is that okay?
Yeah, fine. No problem.
Okay, so I just wanted to go back to another question that came on the planetary nebulas, nebulas in general. What are the different kinds? And Akarsh, you wanted to take that?
Yeah, I can take that question. So nebulae in general, the word nebula is used for a general cloud of gas. In the past, people thought that galaxies were clouds of gas, that they could not that they could not resolve many details in or so on because of the lack of power of their telescopes. So they used to call them nebulae, but that term is more and more obsoleted now. So today, when you say a nebula, you normally mean a cloud of gas. Now, it could be a cloud of, I guess, gas and dust. So if it's a cloud of like colder molecular gases, or I think they call them dust in astronomy, I'm not 100% sure, then that will block the light of what is behind it. Then it's called a dark nebula. So that's the first type of nebula. Like Horsehead Nebula, example of a dark nebula. Second type of nebula is reflection nebula. This is where the light from a star is reflected by a gas behind it, and you are able to see the reflected light. Or more correctly, scattered light. So that scattered light is bluish in color, just like the sky is blue, right? And so that object is called a reflection nebula. Then there are emission nebulae, which are emissions from hot gas. Now, emission nebulae themselves come in many varieties. They can come from the birth of a star, that is, the gas in the galaxy starts glowing and gets ionized, and then you can those are the star forming regions like Orion Nebula and so on. Those are called H2 regions. That's a kind of emission nebula. Then there are things called supernova remnants, which are the end of a life of a star, when it ends in a supernova and it releases all the material that is present in it as a gas. An example is Crab Nebula, Whale Nebula. These are supernova remnants. They will generally have very sharp filamentous structures that correspond to the shock waves and other things that came out of the supernova. if the star ended its life in the white dwarf phase rather than becoming a supernova, then the outer shells of gas in that star tend to become what is called a planetary nebula. It expels a shell, and usually those tend to be circularly symmetric, or they are bipolar, and I don't fully understand what mechanism causes one or the other. And those are planetary nebulae. So there are a few other kinds of nebulae, but I'm not very familiar with them beyond this point. But the general classification is dark, reflection, and emission. And within emission, we have H2 regions, planetary nebulae and supernova remnants. Then there are a few others in radio and so on, but that's kind of irrelevant to optical astronomy. So.
Thanks, Akash. I think that summarizes most of the nebulas, I'm assuming.
I want to add, there's a follow-up question. Crab Nebula is a supernova remnant. It's not a planetary nebula. Yeah.
So the Ring Nebula in near Vega, I think that's a planetary nebula, right?
That's a planetary nebula, right?
Very beautiful nebula, actually. I would highly recommend anybody who wants to see a stark difference between planetary nebula and a supernova nebula. So really nice to see.
In fact,
right.
I would put it up in a, if you are a new person and you want to understand these nebulas, just consider you have a cloud, and what are the different ways you can see the cloud? If you have a cloud, and if the source of light is behind the cloud, then the cloud is getting illuminated from the source behind. That becomes your reflection nebula, because it is reflecting the nebula. If you have a cloud and there is a light source behind, okay, this is a cloud and light source is behind, and the cloud is blocking the light source, it becomes a, what was the word that Akash used now?
A dark nebula.
So one is reflecting, the other one is dark. Why is it dark, called a dark nebula? Because it is blocking the light and there is a dark patch that gets created. Okay, so you understood the name. Now, similarly, when the star is getting formed, here you see a picture, the light here, the nebulosity that you see or the cloud pattern you see is because there are new stars formed, and that new stars are reflecting the light in these, by these clouds. Okay, that is where you have a Ware nebula. Now the light reflected because of the supernova, the remnants of a supernova, that is at a different energy level. So that is called as supernova remnants. Planetary nebulas are typically found after the nova. We call it as just the nova, where giant red stars, they tend to give away their outer shell in the end of their life. And these outer shells are shelled out because of the variations due to the gravitational force and the mass of the dynamics of the star in its end stages. So it's constantly give away the outer layers, because a dying star, giant red star or a red giant star, cannot hold on to its outer surface. So that gets off. And now that forms a ring nature or some kind of a globe, some kind of a spherical structure around the dying star. You can see this kind of patterns around dying star, that is a nova. Second one, you can also see through around a star which is a white dwarf. So you don't see a white dwarf, but you see this. So basically that's the end. The white dwarf has already given away all the materials and it is just at the core. So that is what you see. Ring Nebula is a classic example of a white dwarf in its shell given out. Helical Nebula is one more very interesting one. Or Helix Nebula, yeah. Cat's Eye Nebula. These are all beautiful nebulas, which are, the shells are given. Yeah.
All right. Yeah, thanks for that. So I do want to go back to Rajpal's question, and there are more interesting questions coming in. Actually, the RA declination, the coordinate system question is, I think it's also super, super important. So, but I'll go in the chronological way. So coming back to Rajpal's question. So if I understand your question properly, just wanted to, put it in the right context. So you're saying, how do we know when we see the light of a very distant galaxy? How do we know is the galaxy still there? Is that the question, or how do we know this light has come from that galaxy? If you can, pinpoint the question again.
I know I would give the answer to this question and also explain.
No, actually, I was not clear about the question itself. Rajpal, exactly what did you want to? If you can please repeat one more time.
Just what I was trying to ask is, if they are saying they saw a image which was at the beginning, that was 13.2 billion years back, right? So now they don't know whether that galaxy is still there, or it is moved away, or it is moved away, or it is still there. I mean, we don't know. So they say Hubble cannot see beyond that. So like what I want to ask is, if it is not there, if the galaxy is not existing, over a period of time, the light emitted from that galaxy or something, whatever it is, over a period of time, the intensity and something dies down. The intensity dies down, and there are a lot of obstructions also passing from such a great distance. The light what is passing takes a.
Yeah.
I don't know how to explain. I mean.
So is your question then that how is that light
able
to reach to us?
Light, yeah.
So is the question that how is the light able to reach to us, because it's so far away, there's so many obstructions in between, but still it reaches us somehow? Is that the question?
Yeah, more or less. I just want to know, like,
okay.
If it is not existing, how we are able to find out that still that it was 13.2 billion years or something ever existed.
Okay, so there are 2-3 questions mixed up here. I would say, Naveen and Akrish, how do we age? How do we come to know about the age and distance? How do we derive age from the distance, etc.? And also, what is the furthest point we can see? And is these galaxies, distant galaxies, still there when we see? So there are 2-3 questions, I think, there.
Yeah, I think there was one more question within that. So, whatever article which Rajpal was mentioning, so it says that it has captured the galaxy that is like 13.5 billion years ago, but we can see that image. But now, if we want to see that again in the future, we will not be able to see, because and why is that we will not be able to see is one of the question what Rajpal wanted to answer.
Okay. So I can answer the question on how we know how far it is, what is the limit on how far we can see, and how the light reaches us with all the obstructions. So the thing is, it looks like the space itself is very transparent. It was not like this, but at some point in the history of our universe, the understanding is that the gravity pulled various gases together to form galaxies, and so the space in between is transparent. So if you use a more and more powerful telescope, you can look at fainter and fainter light, and the galaxies are extremely luminous. Some of them, they are called active galactic nuclei. There's extremely luminous, some of the most energetic things, probably the most energetic things in the universe. And so sometimes we can see these galaxies even at extremely high or extremely high distances, right? That is that is one part. So we can see the light from them if we construct a big telescope. Not all the galaxies at that distance, but specific bright ones are easier to see. Second thing is to measure the distance to those galaxies. What we are measuring is not actually the distance, but a parameter called the redshift. The redshift is an so when you are sitting in let's say you are sitting in a train that is stationary, waiting for another train to pass. When that other train passes, you see the train horn does this thing where it's the pitch of the train horn goes up a little bit and then it comes down as it goes away, right? So the pitch of the train horn changes depending on the speed of the train as perceived by you. And that phenomenon is called Doppler shift. The same thing happens with light also. Things that are moving away from us, the light from those objects tend to be shifted towards the red color. So we call that red shift. So there are certain materials in the universe like hydrogen, and we know that hydrogen, when it emits in a certain way, it emits light of a very specific wavelength. Wavelength is like pitch of the sound. The same notion of pitch of the sound is the corresponding thing in light is frequency, or you can think in terms of wavelength also, but one of these. And hydrogen emits a light of a very specific frequency that we know on Earth and we can measure. So when we look at the same hydrogen in a very further, very distant galaxy, we can see that frequency of that hydrogen light will be shifted either to the red side or the blue side, depending on whether the galaxy is going away from us or coming towards us. Because the universe is expanding, this is something that we just know as a fact. Because the universe is expanding, the galaxies that are further and further away are going away from us at a higher and higher speed. And that we measure as the redshift. And so based on that redshift, we are able to say that the galaxy, when it emitted its light, was 13.2 billion light years away from us. And that is how we are able to say that light is 13.2 billion years old. So that's how the determination is done. What the galaxy is doing now, we don't know. But chances are it is still, actually we don't know. 13.2 billion years, we have never studied a galaxy, or maybe we can have some theory of what is happening, but that light is still coming to us slowly. So even if the object that is emitting the light is not there, the light is still coming. It takes time for the light to propagate, so we are still able to see it.
So whatever we are seeing is the story as it happened when it happened, like 13 billion years ago. So we are looking basically into the past. That's what we are saying.
That's correct.
Right?
Let me give you a generic explanation apart from what Akash was saying. Let's assume a situation. Let's take a human life cycle. Okay. Now, in a human life cycle, let's consider a parameter. How much distance in a given time a human can move, a baby can move. So let's take a condition. When the baby is just born, you give some time. What is the distance the baby can move? 0. Okay. Now, as the baby gets to 1 year, it can move a little, maybe about 5-10 feet. When the baby gets into 5 years, it can move a little more. And when you are an adult, you can move far away. Like maybe in a given 5 minutes, you can go probably about a kilometer faster. Okay. So that means as you get closer to the youth, you can move faster or you can move larger distance. Now consider this as a redshift. The moment the universe is formed, the redshift is 0, minimal or 0. And as you get to the current world, you see the objects which are very close to us, they are moving at a redshift larger. Now what happens? They are moving faster, covering larger space. Now, the objects which give us redshift between, let's say, 25, 30, or up to 1, 2, they are all within 1 billion light years away. When the redshift goes to somewhere around 3, you are actually seeing about 2 to 4 billion years away. When I say redshift now, you have to assume like I'm going and looking at the younger generation people moving around. Okay. As you go closer to the redshift of 0, you know that it is oldest one that you're seeing. And as we know, the universe itself is about 13.11 billion years old. The redshift leading to 0 means it is at the origin of the universe itself. That means it is closer to getting to 13.7 billion light year, 13 billion light years away. Okay, but actually its distance could be that from its beginning till now it would have traveled much more. Okay.
Yep, sure. I think we are at 2:30. I think this can, I'm sure this can continue. I hope that answered your question, Rajpal. And I don't know if we should take one more question on the RA coordinate system, or should we close it out here? But what do you think?
I'll just give one more, a very simple answer, so that Rajpal would also think in a different angle along with others. Let's assume the spectrum of electromagnetic wave. We have high energy waves, we have low energy waves. Now, every object will radiate across all these spectrums. It is just that black body radiation, it has one preferred, one place where based on the temperature, it will radiate more. Now, in the initial stages, these energies that were radiated from the early universe, they are so high they can travel a longer distance. But as you rightly said, Rajpal, when they are traveling through the space, they will lose energy. But it is that higher energy particle which will lose energy faster. The lower energy particles will not lose energy faster, and there will be a shift. And that is what Akash was explaining, that the hydrogen has its specific signature. That frequency gets shifted. Okay. Now, if hydrogen, let's assume that hydrogen energy of the light emitted by hydrogen was visible in the visible light. Okay. As it passes through the space, its energy will get lesser and lesser, which means I will not be able to see it in the visible spectrum, but I can go to the infrared telescopes and I'll be able to see. The object is not visible in the optical range, but it is visible in the infrared range. Now, if you go beyond, in the far infrared, it will be visible, even though infrared stage, it is invisible. So it will not go invisible like this. It will go invisible across the spectrum of the electromagnetic wave. So now, if something is visible in the very low energy level, that means it has traveled a lot of distance. That is one of the ways that you can find out the existence of these things. Yeah.
True. So it goes from optical to infrared, and then finally we reach the cosmic microwave radiation beyond which we cannot anyway see, because that's our pocket universe. So we are contained in that. I think that's probably what's coming out. I think we can, yeah, I'm sure this is, I think, a very huge topic in itself. We can actually do a separate session because there are many interrelated concepts. Rajpal, I hope it answered. Otherwise, we can again, continue offline, or maybe do some more sessions. I think I would probably take one last question and then we wrap it for today. And I don't know, Shashi, if you want to take that, and others also, please feel free if you want to chip in on why do we have two coordinate systems, the equatorial versus azimuth, and what are the benefits, pros and cons, and what does it mean for a beginner?
Okay, so there were three questions there. Let me try to deconstruct it. For a beginner, coordinates are a way of finding objects, and for the most part, coordinates are no longer necessary because the software takes care of it. And amateur astronomers, either if you're using a go-to system, the software has a database of objects and their coordinates, and it can take care of it. And if you don't have a go-to telescope, chances are you're star hopping, and the software has already done all the computations to make the star map, or people have printed a star map. So again, no, familiarity with the coordinates is not necessary. The most that amateurs have to deal with the coordinate systems comes with in two places. One is how their mounts are designed. This I will let somebody else answer on the mounting part. The second place where you deal with coordinate systems is to describe an object whose catalog number you don't know, or whose catalog number you want to find out and enter into your software. That's when amateur astronomers deal with coordinates. So, for example, your software might have NGC objects, your software might have IC objects, but chances are it will not have some unusual catalog like, let's say, DDO, which is David Dunlop Observatory catalog of dwarf galaxies. This is some rare catalog that, it's a catalog of dwarf galaxies. But let's say you want to observe something that is listed in that catalog. Then you can find out the RA and DEC coordinates of that object and enter it into your software. So that's the extent to which amateurs deal with coordinates, unless they want to actually do some calculations and so on and so forth. Now, the coordinate systems, there are any coordinate system that describes a position in the sky needs two angles. This is the case. Every coordinate system used in astronomy has two angles. One goes up and down, if you like. Imagine the picture of a globe. One of them goes up and down, and the other goes around the globe. Okay, just like latitude and longitude. So the equivalent of latitude and longitude in astronomy is sort of RA and DEC. RA is like longitude, and declination is like latitude. Now, of course, it will take a lot of background to explain how these coordinate systems are constructed, but the RA and DEC coordinate system is designed such that instead of being fixed to the Earth, it is more or less fixed to the sky. So objects in the sky generally have fixed RA and DEC, generally, to good approximation. Okay, I should put all of those caveats because there is a very slow effect called precession that does change RA and DEC. But over 2 or 3 days, 4 days, 5 days, RA and DEC of a star remains constant. Okay, to very good approximation. The other coordinate system used is alt-azimuth, which is fixed to the observer. So that is very easy to understand. If you are going outside and looking at the sky, you move your hand up and down, that is altitude. You rotate left and right, that is azimuth. As simple as that. So when we say an azimuth of 35 degrees, depending on the conventions, there are many conventions, unfortunately. But in one convention, azimuth of 35 degrees means now look at the north, like the cardinal north point below the pole star on your horizon, then turn 35 degrees towards the east. That is the point azimuth equals 35 degrees. Then let's say the position of the star is 30 degrees in altitude and 35 degrees in azimuth. Then you first move the 35 degrees in azimuth, and 30 degrees in altitude simply says tilt your head up by 30 degrees. So that's the alt-azimuth coordinate system, which is very natural to an observer. And there is a huge mess of operations that needs to be done to convert from RA DEC to alt-az, which is something that every software does. But I think, let me answer the question. If RA DEC itself is changing of a star because of this slow effect called precession, then what can we do to determine the positions of stars? And the answer is that there is a fixed reference frame corresponding to a particular time. I think the time is approximately January 1st, 2000. I can't remember whether it is midday or 12 o'clock in Greenwich or midnight in Greenwich, but it's around it's some time in 1st January 2000. This has been taken as a standard, and all the positions of objects that we know, stars and so on and so forth, are calculated to this particular the RA DECs are calculated for this particular date, and that's what you get as the J2000 coordinates or ICRS coordinates. Now, what is the difference between how is this reference created? Earlier, people had catalogs of stars. This is what is called FK4 and FK5. There were catalogs of stars whose positions were together combined to give us a sense of where we are in the thing. It's as if we are using the stars like landmarks in the sky to figure out where things are. Now that has been replaced by using very distant quasars who don't have as much motion of their own, because it's just like this. Even if a bus is going very fast at a very large distance, you don't see it move much because of the angle change is very low, right? Whereas if the bus is moving right near you, it zips by. So that's why the more distant you can pick a reference for this, the more solid your landmarks in the sky are, and that's why they use quasars to do this. So that's how the reference frame is fixed. I hope I answered that question. I know it was a very technical explanation, but it was also a technical question. So I can clarify further if necessary.
I would put in a non-technical term now. Okay, Akash. Okay. Whenever you want to learn about coordinates, you need to ask just two questions. The object that you're looking at the sky, do you want to tell about it to somebody around you, or do you want to tell about it to somebody who's in a different location? If you want to tell the object's location who is just around you, then altitude azimuth, which means move your hand up and down and right and left. That coordinate system is suitable for telling that, okay, look in this direction for the people who are just around you. That means the altitude azimuth is a local coordinate system. Now, if you want to tell it to somebody else who is in a different city, then you need a reference. That reference cannot be a local reference. That reference has to be a common reference. That common reference, we take it from the sky, because the star's positions in the sky is relatively fixed. So we take a reference of a star. Example, if I have to tell you locally, I will say, look straight and turn 30 degrees towards your right, you will see the object. That's altitude azimuth coordinate system. Just turn right and then see. If I have to tell you, look at the series. So the constellation Ursa Major, look at the star series. From there, I want you to go down. And if you go down by 4 or 5 degrees, you will find M41 open cluster. That means I have to give you a reference from the sky to point to the object. And this can be anywhere. You can be in Bangalore, you can be in London, you can be in US, you can be in any location on the earth. The reference will almost be the same, because from the sky, everybody has the same reference. Now let's go to the second one. I don't want to tell anybody this location, but somebody has seen the object. I want to see it. Example, Messier has seen an object M110. Now I want to see that object. He is not in my location. So what coordinate will help me? The RA and deck. That is the reference in the sky. So all these catalogs, they are not reference to your local place. They are reference to the sky, because that can be used by anybody across the globe. So now you need to ask, am I talking to somebody who is local, or am I talking to somebody who's in a different cities, in different location? The different location always has altitude and the right ascension and declination. That is called as RA and deck. That is where you will find all the coordinate, all the catalogs. They will only have RA deck, and you have to convert it into local time if you want to look at it in the altitude and azimuth. So there are two types of mounts. One mount is RA deck mount, that is equatorial mount. The second one is altitude azimuth mount. So in fact, in altitude azimuth mount, the processing unit, the computer, will actually convert the RA deck position to the local altitude azimuth positions for every time you point to the object. Okay, so those are the two types of mounts as well as the coordinate systems. I hope that.
So yeah, that was a very good, very nice explanation, and I mean that is really helpful. And Akash, so I'm wearing a beginner's hat here. So are we saying when we have a go to scope, which system does it follow? We have mounts that can follow both the systems. And if yes, then which one does one prefer? How do we make the choice?
Okay. By default, if you have a go-to system, it does not matter which mount you have for your observations. If you are an observer, it does not matter what type of mount you have, be it equatorial, be it alt-azimuth. If you are a photographer,
sorry, I meant for photography. Yeah.
For photography, it does matter. So for photography, it does matter, and the equatorial mount is what is preferred and good because of the field rotation problem. You will get altitude azimuth. You will have a field rotation. That means what do you mean by field rotation for people who are very new? Look at moon today when it is rising. It will be in the east. Look at the shape of the moon. And when it is setting tomorrow morning, because it is very close to the new moon now, full moon now, you will see that you'll be able to see the setting moon. So when you start seeing the setting moon, it will move in the west and it will be like inverted. Kind of a shape in the moon, that rabbit hair will be on the top when it is rising, and when it is setting, it will be down. That means it has inverted. Now, the same problem happens when you use the altitude azimuth. It starts it is called as field rotation. We want to avoid that. And also in altitude azimuth, we need to track on both axes. So we don't want to do that. In the equatorial mount, it is fixed to the orbit of, it is fixed to the pole of the Earth, the rotation axis. So you have to only track on one axis, and that is much easier and much better. So there is no field rotation problems coming up there. So that is why we prefer an equatorial mount astrophotography.
Cool. And I think we can probably again deep dive into this topic when we do the session on astrophotography, I assume. So, but I think that summarizes the question. So thanks, Naveen. I think we are off out of time. So I would probably say let's go around the table again. If you want to give one last closing comment, I just want to go through the panelists again and see any closing comments, and then we call it off for today.
Satish, so there is one more point that I wanted to add on the coordinate system. So even if you don't want to follow any coordinate system or all those complications of converting from RA to DEC, so the best way is like say how you are describing the address of your home. So you don't say okay, go straight, go left, or rather if you don't want to get into the exact lat long. So you have a specific thing called as an address. So you say your building name and this one. So something that can be similarly applied to the deep sky objects. So say you want to look at say M36. So all you say is okay, it's in the sun, somewhere in the center of an constellation Auriga. So that is a much simpler way for the beginners. And then then you can start developing the coordinate system.
True. So you're saying we start with a landmark, and first find the landmark, start with that, and then make your own star hopping patterns, and then go out, experiment for yourself. And I think that's a good experience by itself. I think, yeah, agreed. That's good advice. So, what would be your closing comments for anybody who's starting and who has probably heard this session, or they will hear this session later on? Any closing thoughts or remarks?
Okay, I can go first on this. So, so they don't don't try to jump into buying any telescope or anything first. So try to set up your expectations, meet people from a local astronomy club, join their star parties. So we have one that is coming up in the month of February. So so that's a great place to get together to know more about the deep skies. So this is something that I wanted to say.
Yeah, I would second that, and I would just say it is good that you get started. The very fact that you have watched this video as well as you have been in live here so far is indicating that you have a lot of interest for people who have watched this. The next step that you could do is try to contact us, join our Telegram channel, WhatsApp group, and then try to ask as many open questions as you have so that we could actually help you out and share our learnings. So when you start learning, you share to the other people and you learn from there. So get started, and Amateur Astronomy Group is never hesitant to share their equipments, especially when we're observing. So you should not invest immediately. You should observe through the other people and then get to the buying part of it. Okay. And of course, this is a season usually between November and March to April is a season where we go out and observe and do a lot of observations through the city as well as outside. So you should join those groups. Yeah.
So I can go next. The first thing I want to say is when I started in this hobby and walked into ABBA, there were about 30 new terms that I have never heard in my life before, thrown in every 10 minutes of conversation, like Messier object or deep sky object, planetary nebula, Altazimuth mount, 180 grit, M6 bolt, even that, and and all of that, right? So there is so much in the spectrum of this hobby, starting from. So it depends on how you get into it, right? Let's say you get into the ATM side of things and then build a telescope to do visual observing and photography. There is just so much to learn, both on the astronomy side, on the DIY side, on the photography side, signal to noise ratios, and so on and so forth. And on the observing side, how do you do the correct magnification and averted vision and so on. It's very easy to get turned off by the terminology. I'd say take it slowly. There's a very sharp learning curve. And this is why I guess everyone has mentioned it's nice to start without equipment and learning. I actually went against this. Like I mentioned, I started with an 8-inch telescope. I did not go with binoculars. But basically don't get carried away by terminology and or don't get confused by terminology and equipment, and start simple and start slow. It takes a while to build up all the context. I think that's everything I want to say. But in my experience, this hobby has been extremely fun, and it also sucks you in really badly. And you will probably find your own niche, what you like and what you don't like, and it's perfectly fine. It's a hobby, so it's perfectly fine to do what you like and ignore what you don't like, right? So that's my concluding remarks.
Yeah, so I would
Thanks,
like to say
Akash.
that, so for people who would like to get into visual observing, it really helps to make good use of your time under the stars, right? Because in the places that we stay, for example, Bangalore, we get about 4 months in a year to actually get under the stars and observe. And even in that month, we have to go on only specific days when the moon isn't around. So it helps to actually buy a scope and spend some time actually collating the number of objects that you want to see before going into the dark sky location. Because oftentimes I've seen that people just buy a scope and come to the star parties, but they have no idea what to see and where to see. So if you have some kind of basic list with you and some kind of ideas to where the objects are in the sky, you will make use of your time much better.
Thanks, Shashi. Yeah, so thanks for all the closing remarks. So I would just also add some closing remarks to this. I would say one is I think people have brought in so many points. I would say also don't forget to have fun. For me, I think that's one of the things. It's all about beauty as well. When you look at the sky and the stars and the constellations, and if you are able to find a deep sky object on your own using a manual scope, it's an amazing experience. So the fun aspect is, I think for me, it's important, because sometimes we may get carried away so many things with so many technicalities involved that the fun gets aside. So that's one thing. The second thing also is, make sure you carry the curiosity. I think for me, the curiosity is the most important thing in this, and in any science. It's very easy also to sometimes we keep the curiosity aside, and then we become very, with the instruments and things like that, which is also part of it. But I think the curiosity should be what should drive it. At least that's what I think personally. And one last thing is, please give us feedback on how the session was and what we can do differently, because ultimately it should help people who are viewing, beginners, intermediates. So let us know what works, what does not work, so that we can make those corrections for the future sessions. And I do see some other questions coming in, so we'll probably take them offline. So I would probably will close it out for now. Thanks everybody for joining. Thanks to the panelists, and also people who have been here, who are still there and heard the entire thing. So thanks so much for all the questions. And yeah, so see you for the next session, and have a good day.
Yeah, before concluding, Satish, big thanks to you for coming up for this idea and moderating the questions and taking up the responsibility. And big thanks to Sudash and Kirti also for all the background work, segregating the questions and everything. Awesome, guys. And we would definitely want to conduct similar sessions in the future. So be tuned. Yeah, thanks for that. Yeah.
Yeah. Hey, thanks for those call outs. Yeah. Thank you so much, guys. See you then. Take care.
Thank you.
Bye.
Thank you. Bye.